The earthquake hazard in Southern California is larger than anywhere else in the United States for two reasons. First, we have over 300 faults. But second, and equally important, we have 10 million people just in Los Angeles County alone. And we have a lot of buildings and a lot of infrastructure being subjected to those earthquakes. Just in Southern California, we will have 20 or 30 earthquakes today. We record about 15,000 earthquakes a year. Most of them are too small to be felt. We have a felt earthquake a couple times a week just in Southern California.
Continue on the current road.
Right now we're coming up along the San Andreas Fault. It comes right through these hills, and along that section of the San Andreas Fault there's compression, and that's building up the mountains that you see as we drive along here. You see the red and gray banding. This is the San Andreas Fault. The San Andreas Fault concentrates most of the motion between the North American and Pacific plates. And so the San Andreas Fault has been the source of the greatest historical earthquakes.
Approaching destination on the left.
This section of the fault last had a big one on it in 1857. And so it's stored up plenty of strain, and so the next big earthquake could happen any moment. Could happen even as we're driving up to it right now. You just never know.
Earthquake forecasting is a difficult subject. We want on human timescales to say there's going to be an earthquake next week or next year or in this decade. But the faults are moving on timescales of hundreds to thousands of years. So we cannot, at this point, with any of the information we have, tell you what will happen this year. What we can do is look at where the strain is accumulating, which faults are getting stressed on the very long term, and say these are active faults. That doesn't tell us they'll happen this year or this decade, but it does tell us that on the long run, this is one of the faults that's going to be moving.
You have arrived.
The global positioning system gives us a unique new capability for measuring the very slow, steady accumulation of strain on the fault system. The seismic instruments that we've used for many decades to study earthquakes are particularly good at measuring the shaking, but not able to measure the plate tectonic strain. The Southern California Integrated GPS Network is this array of 250 GPS stations throughout Southern California. Half of the nation's earthquake risk is in Southern California, and about a quarter of it is in Los Angeles. So that's why we've gone ahead and put in this new state-of-the-art monitoring system here. The GPS array works by receiving satellite data from all of the GPS satellites that are in view. By doing that, we can then position each site very precisely. And through time, we track the positions of those points, so we see the strain building up on the whole fault system. When an earthquake occurs, the stations all move, and we measure that as well. The vehicle navigation GPS receiver is much simpler and just takes part of the GPS data. So it positions within about 20 feet, whereas this kind of GPS equipment here can position to within about 1/8 of an inch. This station was installed a couple of years ago. So within those 2 or so years since it was installed, it's already moved by about this much. This whole mountain that we're standing on has moved towards the northwest by about 4 inches with respect to the interior of the North American continent.
With a GPS network, we essentially are just measuring the location of points. So we can take 2 points on the Earth, and we see how they change. So as these points get closer together or farther apart, they tell us about that elastic energy that's being stored up and how future earthquakes may behave. We take those data and we put them into computer models. And in the computer, we can speed up time and run models that go for thousands of years, and then display that visually so that we can see fringe patterns, and where there are earthquakes, there are fringes, and the bigger the butterfly pattern that you see, the bigger the earthquake that has occurred. Each color fringe is about 6 centimeters of motion, so you can actually go count those fringes and find out how much motion occurred. Then we try to understand how the whole fault system behaves and how earthquake faults interact. One of the very interesting things we've learned is that one earthquake can speed up an earthquake on another fault and make it happen, or actually turn off an earthquake on another fault. And that's very interesting, so we need to use the models and the data to understand the fault systems.
So we're hoping to use GPS to zoom in on where the hazard is the greatest, especially in Los Angeles. Because there are so many people there, we really need to map the strain and the hazard in more detail. Engineers do know how to make buildings withstand earthquakes, even very strong earthquakes. So if we have better information on seismic hazard, that can be used to help guide a retrofitting program to take down seismically unsafe buildings and replace them with safer ones.
Space is really revolutionizing our understanding of earthquake processes and plate tectonics. We're just now getting hints and evidence of things that occurred that we never even knew happened before. So it's very, very exciting. And I think the next 100 years will take us way beyond what we know now.